All right, now I am recording. Great. Okay, so I had a lot to go and I only got through the first 3 chapters and some pictures in 4. So, and 5 is what it was last time. So we're not getting as far. I'm not getting nearly as fast as I'd like to. Anyway, we've talked about the abstract. We're on section 8. Okay, so back to the theory of information via Claude Shannon and physics. How many of you used to watch the Johnny Carson show?
Not
once
me.
a while.
I have.
Yeah.
Okay. Did many of you watch the telephone game?
No.
No.
Oh, that's too bad. It was really fun. They would have a bunch of guests who would be sitting at a chair, at a sofa, and at one end, someone would whisper into their ear the message. They always had people who had different languages possible. So there'd be somebody in French, somebody in Italian, someone in English, etc. And so somebody in English would start it, say it to say somebody in French. The person who was in French would be able to tell it in French to somebody else who knew French and Italian. So the person who was French could speak the result in Italian. The person who knew Italian in English would say it back in English. And so you had the long string of translations. And it was always hilarious what the resulting translation was after the sequence of language changes. So this is an example. In English, you say the spirit is willing, but the flesh is weak. But in Furbish, it's tui sa moko ga no ta fa soso. And then when you try to translate that back into English, it comes out the wine is acceptable, but the meat is underdone. So it is, all of you who I assume know about Furby's picture of a little animal who, if you would speak to it, it would repeat to you in Furbish what you said. It was a Japanese toy, quite successful in the 90s, I believe. Anyway, so translation can be, meaning does not necessarily go with translation, as we've talked about last time. So what am I trying to do? I want to try and identify the universal ideas about information. These are in some sense parallel to category theory, which my own personal comment is general nonsense, but a lot of mathematicians, in fact, are thinking they're going to get rid of equations and use category theory, that is equivalences, instead. And most of the important work that's going on in mathematics right now is in category theory, so whatever. But a reasonable question is it useful? We're not right now trying to quantify information, although by the end of the lecture we will. And a single quantity may not be enough to capture all aspects of information. As we've pointed out, meaning is not the equivalent of a message. Meaning is observer dependent, and hence different for each observer, very special relativity-like. Nevertheless, we can find some useful information to describe information, useful quantities to describe information structure. There's three heuristics. The first is physical. A Jewish physicist in Germany, Landauer, left Germany in the mid 30s and became rather important in information and in thermodynamics. And he always said that information is associated with the state of a physical system. So the information you're hearing right now is either being sent over various electronic systems getting to you. My voice is being communicated over physical systems. So all of the information is always associated with the state of a physical system. Information is also relational. Information refers to the relations among subsystems of a composite physical system. So that's a little harder to get to. We'll get to that later, but I hope you at least get the sense of it. We've talked about it being fungible last time. We showed that you could have music in the form of a record, a tape, a CD, memory, you name it. So information can be transformed from one representation to another. And information is a property that is invariant under such transformations. Everybody remembers about invariance, right?
Yeah.
Okay. So we have discussed invariance quite a bit along the years. Will somebody please define invariance? Somebody other than Steve. Bob? Bobel? Art?
No chance. No chance. I'd recognize it if I saw it, but I can't tell you about it.
Okay. Chaz?
Same answer.
Thanks, Chaz.
I couldn't understand what he said.
He said it's the same. He said it's the same answer.
Well, yes.
How about if it is something which is not changing under any kind of condition of transformations?
Okay. That's much better. Yes.
See, that's why you need a woman.
Thank you.
Absolutely.
Only then?
No, I can think of some other reasons too.
Okay, so will somebody please give me a physical example of an invariance?
My wife.
Okay. That's accurate. All right.
Breast mass.
Rest mass, yes.
Could you just give us an example of invariance? with the music?
Well, yes, that is an example of invariance. The one I'm particularly thinking about is topology, and in topology, there is an invariance. If you remember the old joke about topologists, topologists are people who don't know the difference between a coffee cup and a donut. And the invariant of a manifold, the only thing that is important topologically about any manifold is the hole in it, the number of holes in it. So the reason that a coffee cup and a donut are invariant is because they both have just one hole in them. And you can continuously deform one into the other. So that's a math invariance, and we've done a lot on manifolds, as we talked about general relativity and a lot of other parts of physics. And this is something that should be, we've talked about this particular example, I know, at least a couple of times. So anyway.
Bob, just a question on, it looked like when you deform a donut into a cup, you have to tear it to get that hole in the top of the cup.
No,
No, you don't.
you don't. If you look carefully, you'll see here it's solid, and then the edge comes going down, filling in the bottom and then going back up to the top, making it solid.
Oh, okay. Yeah, if you had a hole in the bottom of the cup, then there would be two holes.
Right, and it would not be then you'd be a different object. You would have a two-hole torus. Anyway.
I say something. It looks like with the whole versus the non-whole, you're talking about matter, an object with matter versus not matter. So in other
I'm not
words,
hearing her very well.
I'm sorry, it's my fault. Is that better?
Yes,
That's
much better.
Yeah, it's my mic. I forget to put it down. With this example, with a hole, it looks like you're comparing, or you're talking about matter versus not matter in this object.
Well, yeah.
I mean, you have two things in this object.
For mathematicians, this is just an object, but physically, yes, you have to have the distinction is about the hole in it. So in the cup, there's a hole here, and when you distort it, you go into a hole in the donut.
Okay.
So if this was a real massive object, yes, this would be the importance is the location of a puncture in the material.
I guess what I'm thinking of, I mean, it brings to mind all kinds of things. 2 holes, 95 holes, not a hole, but an inlet, if you will. In other words, the matter portion does not create a hole with the matter all around it, but just an opening in it.
You mean like the part coming in
Yeah,
here?
in effect, yes.
Right,
So how does
okay.
that play in?
Well, the only thing that matters is the puncture. That's the reason I actually use the language. In topologists, they talk about how many punctures there are in a manifold. And you have to go through, you have to puncture the entire manifold in order to change its topological invariance. So with a donut, there's one. I didn't have any more pictures here. If I had realized this was going to come on, I would have had some extras to show you. But you can have a donut that has two holes in it. You put a hole on this side, and you can do 3, you can do n. And all of them are different objects. They're the differences between objects. So you always have to have a puncture. That's the only thing that matters, is the puncture all the way through the material. Yeah.
One way that I've seen this example expressed is if you took yourself just a solid glob of clay and you put one hole in it, then I could, by just manipulating that clay, nothing more than squeezing it here and squeezing it there, I could either make a donut or a cup out of it. I could never make the thing that Bob Lukuski suggested, and that was a cup with 2 holes in it, without putting another hole in it. So if you just consider this as clay being manipulated any other way, that hole is always there, whatever form you want it to take. That is that particular object with 1 hole. 2 holes, you can make something else out of it. So if you think of it as cushion clay, maybe that will help sink in.
Okay. Yeah, that is another way of talking about the same thing. But always the importance is the number of punctures
Right.
all the way through in the clay. Okay, what is information? Well, you start with a series of messages, for example, news. There might be a newspaper somewhere, but most of the time, or at least for me, all of the newspapers I read are online. So you have to have that collection of messages called a newspaper, made it into electrical signals, which get moved around the internet and then get caught via my Wi-Fi onto my tablet, and then that's where I look at the news. So one aspect of information is a message communicated to a goal, typically an observer. Now,
Bob,
yeah.
I have a question. Can you distinguish information from data? Suppose suppose I collect a lot of data. Is that information?
Yes, no different.
Suppose
Whether
I
it's,
don't.
if you have random numbers, it's information.
Well,
So
Bob, that doesn't make sense to me.
Why?
Well, because
All you have to do is a collection of bits that you want to send along. They can be random bits. They don't have to have meaning. Meaning is something that is observer dependent, not the message.
So, but didn't you conflate data and information? Didn't you say they're the same?
Yeah,
Okay.
that has meaning to somebody who observes it, but you could have random numbers which nobody could understand.
But Bob, data doesn't have meaning. Information has meaning.
No, not in the sense of information theory.
Aha, you have a trick.
Well, as I said, I think in the last lecture, the thing that was brilliant about Shannon was that he went and saw that there were aspects of communication, because he was focused on communication, that were invariant and not meaning dependent. And that was what he defined as information. And it could be anything, including random numbers or data, or, you know, a collection of weather reports, whatever you want to get, you can get it and communicate it. And that was what it was the invariance of the information. His definition was the invariance of all of the messages coming across.
Okay, I'll go away quietly.
Okay, but the communication portion of it ends at the end of the story rather than the beginning, so I'm going to start somewhere else. I'm going to start at the source of information, something that produces messages. Source might be a person, a machine, a natural phenomenon like weather. The messages might be speech or letters of the alphabet or electrical signal or daily high temperatures. In a few minutes, I'm going to suppose that the source produces a whole series of messages, one after another. But for now, let's consider just one of them. How many possible different messages might the source produce? The number of possible different messages depends on the source, naturally. Just as in the previous lecture, I denoted that number by M. Now, M is a significant number because it does not depend on our choice of code. Remember, we talked about how to develop codes that could match the number of letters in the alphabet and a space using bits. Okay.
Yeah.
So, given what you remember and what I've just asserted, why is it that it does not depend on our choice of code, the way in which we transmit or communicate the message? If you remember from last week, we were taking the alphabet, and I showed a table that had the alphabet, an equivalent number. The number could be written in base 2, so it gave a 5-bit code. So what is significant is the letter, but you could send it as a number, you could send it as a sequence of bits, you could send it by having somebody speak and get transmitted over a radio. Whatever you want to use as your code doesn't matter.
So the important thing is there be a one-to-one onto relationship between the source and the code.
Correct. Correct. Okay. So for whatever code I do choose, I'll need at least M different code words. And last week, information is really about the distinction between possible messages. So it makes sense that the amount of information depends on M, the number of possibilities. Now, if m is very small, for instance, let's say just 2, a 1-bit message, then the amount of information in the message is very small. However, if m is huge, then I gain a lot of information when I receive the message. So how you parse the message influences what the messages are like, and also how you can communicate them. Now, a book contains a lot of information precisely because there's so many possible books. We could just adopt m as our measure of information. Could we do that well? Chaz?
What was your question again?
All right, we've said that there's the messages, the total number of messages that we're going to try and code and transmit is m. Is m itself, should this be our measure of information? Yes or no? And if yes, why? And if no, why?
If you picked M as your potential measure of information, it would be obnoxiously large, because the number of bits it would take if an individual book would be, again, M to some very large power. So, but that's not a measure of the information in the book. It's a measure of the potential amount of information you could eventually represent, but not of the information in any given context.
Well, that's part of it. Okay. It doesn't work out, you're right, for thinking about 2 messages from the same source. If we have a possible pair of messages, how many possible pairs of messages if we chose m as the message? The first message has m possibilities. For each of those, the second message also has m possibilities. So 2 messages have m times m, or m squared joint possibilities. And our intuition, or at least my intuition, is that that does not seem to be reasonable. As you said, there's just, the numbers multiply, and my intuition is that 2 messages should just have 2 times as much information as 1 message, not the square of the information. So following that intuition, we need to take the number of possibilities m, which is multiplicative for more than 1 message, and turn it into something that's additive. And the right trick to do that is to use logarithms. Logarithms were introduced into the world by the Scottish mathematician John Napier in 1614. And they soon gained wide popularity as a way of doing difficult calculations. And the genius of logarithms is that they turn multiplication and division into the easier operations of addition and subtraction. And I spent many hours using my log tables in high school until I got a slide rule, which made life so much easier, but you were limited to 3 to 4 digits depending upon the slide rule you had. So mathematicians say that the logarithms are a duality. That is, the functions log and plus are dual to exponential and times. So if you have two positive numbers, r plus is the positive real numbers. So you have two positive real numbers. You can use log to make them into two real numbers. That is, from minus infinity to plus infinity in each case. So if you take the positive numbers and you multiply them, you get a single real number. So multiplication under logarithms, and here, I'm sorry, under exponential, starting from two real numbers, you can take exponentials to get positive numbers. Product of two of those gives you another one. Using the logarithm gets you a real number back. And if you use, I didn't draw this in the right order, I apologize. The arrows are in the wrong direction, but actually these are, oh yeah, these are not ordered, so okay. Yeah, so if you can take two positive numbers, you can make two real numbers out of them. You can add them, make a real number, and go over to a different positive number using the exponentiation. The same way you can do it is to go take two real, let's see, yeah, I did that in the right order, right? So I start with two real numbers, I add them, I get a real number. I use the explanation to get a real plus number. The other way to do it is to start with two real numbers, use exponentiation to get two real positive real numbers, and then you can multiply them and get a real number. And this is the duality or commutative diagram, excuse me, is you can go from here and you can either go this way or you can go this way and you get exactly the same result. So that's the duality of logarithms. I didn't explain that really well. I apologize. Is there any questions about that? Okay, so let's see how it all works. You choose a fixed number b greater than 1, which is called the base. You can raise the number b to various powers. So for any positive number z, you can find that z is equal to b to the x. X is the logarithm base b of z. So if we had minus 2, b to the k is b to the minus 2, which is 1 over b times 1 over b. But log base b of b to the minus 2 is minus 2. Similarly, for minus 1, regardless of the base, b to the 0 is 1. And for fractional, or doesn't have to, just rational numbers, not necessarily less than 1, b to the p over q is equivalent to the qth root of b to the p. But if you have this number, this is its logarithm base p, base b. Okay. Is this,
I find it kind of interesting that b is greater than 1. Is there any use to this system if b is less than 1?
uh,
Suppose you chose b less than 1. You'd
well,
also,
you have a problem if you want to do that, because for various powers, you're going to have different results. So for -2, you're going to have a positive result for the b, but for a odd number, it's going to be a negative number. And the way in which logs are defined is that the number you're trying to add together has to be positive. And any of the cases where this came out negative, obviously the log of a negative number is not finite. So that wouldn't work. You do realize that the logarithm of a negative number is complex and negative.
yes, I know it's complex.
Okay, so that makes it a problem. Okay, so if I'm only working in the reals right now. There's a different definition for complex numbers, and in that you could do it, but in real numbers it won't work. Okay, since a logarithm is just an exponent, all of the basic grade school rules of exponents are also rules for logarithms. So some of the logarithm rules are that the log of x times y is in base b is log b of x plus log b of y. This is one of the things that we showed in our little example of duality. A different type of duality comes from the fact that the log of a ratio of two numbers is the log of x minus the log of y. So you have exponential, instead of times and plus, you have division and minus. Logarithm base b of x to the a is a log b of x. And the logarithm rule for powers, and of course when a equals -1, this is the rule for reciprocals. The log of 1 over x is minus log of x. The log b of 1 is identically 0 no matter what base b. And finally, if x is greater than b, then the log b of x is greater than log b of y, no matter what base we're talking about. Bases typically are either log 2, where they're called bits, or log e, they're natural, where they're called nits, and base 10, where I think they're called bits, if I remember correctly, but I don't, does anybody remember what the bits name is for log base 10? Okay. I think it's DITS, but I don't remember for sure. Anyway, so I come now to the why we're talking about the logarithm. Our information source produces m possible messages. Shannon says the amount of information contained in a message from a source is measured by entropy. And it's defined by entropy H equal to log base 2 of the number of possible messages, m, or the equation H equals log base 2 of m. And you should note that, first of all, the difference between Shannon's definition and Boltzmann's is Boltzmann had a constant, the Boltzmann constant in front of it, and he used natural logarithms instead of log base 2. But as I pointed out before, all of them can be interchanged with each other. In the footnote, you see log base 2 of b to the x is x log 2 of b. So you can take that under two different bases, the same z under two different ones, and solve for what the relationship is, and they're just log 2 of b. So if you absorb the log 2 of b into the Boltzmann constant, you can have Boltzmann's entropy in base 2 instead of natural log. So why do I call this entropy? It's a word that comes from physics, and there is an apocryphal story that Shannon had talked to Johnny von Neumann about his entropy, and that von Neumann suggested that he use the term entropy because they're very similar, except that it's apocryphal. Shannon in, I think it was the mid 50s or so, told someone, you know, that's nonsense. I'd done thermodynamics in school, and I knew where entropy was, and I knew that this was identical to Gibbs entropy, and so I used the same name. Had nothing to do with what von Neumann said. Anyway, so from the outset, Shannon knew that there was a similarity between his measure of information and the important concept in entropy, in thermodynamics rather, the science of heat and energy that we've been studying. In thermodynamics, entropy determines whether a particular energy transformation is possible or not. That is, are they reversible or irreversible? And it turns out when we get to the communication portion of information, you're going to have the same kind of process. There are reversible processes, the ones that Steve talked about, that are one-to-one and onto, but there may be portions of communication which will not be one-to-one and onto, and those messages are irreversible. So we have again, this exact same parallel or similarity. And in in Thermo, you can calculate the logarithm of a certain number, that number being the number of possible states of the thermodynamic system, and that is the Boltzmann's H theorem. So if you go back here, if M is the same as if you put a modified Boltzmann constant in, and M is the number of states in a thermodynamic system, the entropy is identical. Okay, so much for similarity. In fact, we'll eventually get to show that information in thermodynamics is much more than just a similarity. The quantity I've used, H, was proposed as a way of measuring information, not by Shannon in 1948, but by another Bell Labs engineer named Ralph Hartley, 20 years before Shannon in 1928. Hartley's work was an important precursor to Shannon's, and Shannon, of course, was aware of him. He did not call his measure entropy, and more importantly for us, he did not recognize its connection to thermodynamics. Hartley only took a few steps along the path to real information theory, but we should not forget Hartley. He was a fairly important and useful engineer, and perhaps it makes sense to memorialize him in the letter H, and for some reason my footnote is not coming up. The other reason for using H is Boltzmann's H theorem, which is what he used. We talked about this last lecture, that he initially called it E for entropy. There were some people who were objecting to what he was doing and not believing the type of theorem that he was proving, and they kept using the letter H, and he eventually adopted it and called it his H theorem. So either way, we have the same letter. Okay, now the most important question: what does entropy mean? And by meaning here, I don't mean the observer-dependent meaning. I mean the mathematical meaning. So according to Hartley and Shannon, we can interpret H in two different ways. H is the amount of information I gain when I receive an accurate message. That is a measure of the content of the message. Alternatively, H is also the amount of information I lack before I receive the message. So before the message is sent to me, I have a degree of uncertainty about that message. But after that message is sent to me and I observe it, my uncertainty is updated via Bayesian updating that we've talked about several lectures ago. And that second idea, the fact that it's a measure of uncertainty, is interesting, because there's many situations where the importance of a message lies in the fact that someone doesn't know it. So consider, for an example, the idea of a password. Okay. Almost everyone these days has to use one or more passwords for security. I need a password to read my email, or to get money from the bank, or to access confidential records at Social Security, or to buy something online, or even to open my garage door. So there's many, many ways in which passwords are used, but the importance of passwords is that nobody but me knows what it is. So everybody else has uncertainty, but I have certainty. We're starting right now into the start of communication theory. Unfortunately, all I have is the pictures right now. I have none of the lecture that I had planned on putting it here. So we have two choices here. I can just talk through the pictures without any material added to the pictures, or we can stop and continue next week after I've put the remainder of the material into the slides, which I have not had a chance to finish. So which one would people like to do? Either continue and having me wing it, or wait until next week when I have the material added here?
Well, for me, I'm in no hurry, so I think a more meaningful lecture would be more meaningful.
Okay.
I agree. I think that's right too.
Okay.
I agree, and I have an observation to make on this last information or last content that you gave us. It seems to me that you're introducing sentient beings here as far as information is concerned.
No, that's not accurate. Consider in quantum mechanics, which we've talked about the contextuality of observations. And those are true whether you have an interaction between two physical systems, or a system that's set up by a physical, a person who's thinking about how they're trying to measure things. So the sequence of yes/no questions that you start from the wave function until you get a result. Remember, we did the 20 questions where everybody had to choose what they were going to have in the way of a special physicist, and they weren't agreed ahead of time, and everybody had to play the rule that as soon as the person had chosen something that wasn't consistent with them, they had to choose another one who was consistent. And eventually the sequence of yes/no questions would wind up with one unique result. But that's the way quantum mechanics works, whether it's a human being doing the observation or two systems interacting with each other. It's all contextual. So it is not introducing people thinking about things.
Well, could you go back to that slide where you had the definition, and it could be either this or that? Yeah, wait a minute, hold it. The next one. Yeah, that. No, wait a minute. No, that's not the one. It's,
That's
oh,
the one.
that's it with the alter,
Okay.
yeah.
Yeah.
It could be
I
interpreted
was
in two different ways.
right. I happened to use a system where, in the second case, where the amount of information I lacked before, there was a communication to me about a message, and afterwards I had a different uncertainty. So that happened to be about a person, but it doesn't have to be.
Okay.
I mean, inside, a cell, when DNA is split into two pieces and parts of it are copied using RNA to make and grabbing the various, I'm dropping out the word, the
Amino acids.
amino acids that make up protein. All of this could be talked in terms of what's happening as the process of information communicating from the DNA using the RNA as a uh, as a uh, as a transmission, uh, and then the result is a protein. So it doesn't have to be about a person.
Okay.
So Bob, I have a question. Let me just see if I understand that second definition correctly. Suppose we take a password that's 24 characters long, and each character can be either a letter or a number or maybe a special symbol. Let's suppose we have 50 choices altogether. So a 24 character long password, each character being one of possible 50 symbols, would have a total amount of lack of information, you might say, before you know what the password is, 24 to the 50th power.
Yeah.
And you take the log 2, the base 2 of that, and that gives you H.
Right.
So before you know the password, that's the measure of uncertainty. Okay.
Right. Well, that's the measure of uncertainty for everybody who's coming into the system and putting in one. But there's one person who knows what the password is, puts it in, goes to whatever the system is at the other end, and shows that it's identical, and therefore it gets let in to the place they're trying to get into. So, so it's not only, there is it's a measure of the uncertainty that that there is about the message, but it's not necessarily about you. In that particular case, the password, so you have no uncertainty about it, but everybody else in the world has uncertainty about it, leading to, as you said, log base 2 of 24 to the 50 or whatever.
Yeah. Okay.
Well, there always must be, in information theory, a sender and a receiver. And with these two different possible definitions, one of them, the sender alone knows the message, and the other, both the sender and the receiver know the message.
I think you're anthropomorphizing it a bit too much.
Yeah, that's
When I say sender, I don't mean human. I mean,
okay.
we also talked about systems. There can, but there must be a sending system.
Right. So if you have DNA as a starting point of a message, and the process where RNA splits it and makes a copy in proteins, the initial system is the DNA, the transmission communication system is the RNA, and the result is the protein that is made. So yes, you're right. There is now we haven't gotten to irreversible and reversible processes in information yet. That's what's coming into communication next. But there may be portions of the communication which will be irreversible, so that the ending result, the ending message is not identical. It's not one-to-one and onto the message that was sent. And that's what we're going to move into next, about how you can have reversible or irreversible communication systems in information. And if they're reversible, they're one-to-one and onto. If they're not one-to-one and onto, then they're irreversible. Did that make sense?
So I take it you generate microstates if it's irreversible. That is,
yeah.
you generate possibilities which you didn't have before that irreversibly set in.
Right. You had an information, you started the process, something part of the communication system breaks and distorts or fuzzes or changes the bits somewhere, and the resulting message is not identical to what was sent. And that's irreversible. Everybody following that?
Yeah.
Okay, good, good. So any other questions?
Yes, I have a question. Realizing that obviously what you've been presenting in the few, 6, 8 months I've been listening has been this lifelong experiences that you've gained. But this most recent stuff on information theory, is there a specific reference you're using, or just lots of references and you're just compiling this?
Oh, it is a lot of, I started off with a paper by Bill Schumacher, who has has written a paper that demonstrates that thermodynamics starts with information theory, but it's got some very complex state systems definitions that are, it took me literally, I don't know, a week to finally figure out what the hell he was talking about. And that was just page 1 of the paper. So I've been grabbing things from various thermodynamic papers, from books, from I will, at the end, I'll put together a bibliography of material that people can read if they want to.
Okay, thank you. I was just curious. I was away for a couple of weeks, and so I didn't know whether you had mentioned any of that. But yes, I still have some papers that without exaggeration, I know I read 30 times before I started to really understand what in the world I was going to get out of them. So no, I can appreciate that. Yeah.
Yeah, no, the reason I took this on was because I was reading that paper and I was having such a hard time understanding it. I decided I was just going to teach it, and that would force me to learn everything in enough detail as to be able to understand the paper.
This is really very, very interesting. I appreciate all your efforts on everybody's behalf.
I'll second that.
Well, thank you.
Yes, indeed.
Okay, any other questions? All right, then I guess I'm going to first of all stop where am I going to, I'm going to stop recording.